Okay. Okay, everyone. Any questions from the previous lecture or like previous lectures in general? You know, when we were in high school, or I guess not high school, when we were in elementary school, we had like our teachers would designate people to write down the name of people who are talking, and then they would write that on the board. And we had also, you know, the same person would write down the name of the people that they were behaving so nicely. And then they would put an asterisk in front of the people that were really, really nice. So you have like this classroom with people just sitting there, not doing anything, to have like more asterisks. Anyway, so are we good with the material that we talked about in the last class? Okay, so can anyone tell me what is Pauli exclusion principle? And I'm going to ask that in your exam. So can anyone paraphrase what I wrote here?
So each orbital only has 2 electrons with opposing signs?
Exactly. So we show electrons with half arrows, right? Even if you write whole arrow, that won't be wrong. But, you know, for instance, if we have P subshell that has 3 orbitals, every of these squares, we call them 1 orbital, right? So if you have full arrows, you know, and if you want to fill them, I guess the right way to write that is we fill them singly and then pair them up. So if you have the full arrow, it would be kind of like more difficult to write them. So that's why we write half arrows. But if you write the whole arrow, that won't be wrong. Okay? So as your friend said, Pauli exclusion principle says that what I wrote here is wrong. The arrows that represent electrons, both of them cannot be up, or both of them cannot be down. And you know, I graded your extra credit quiz, but my email has been down from 6 p.m. yesterday. So if I didn't respond to your email, that's because of that. I don't have access to my email. So IT guys are helping me to have my account back. So after that, I can upload your grades on Canvas. And I'm going to add that to your homeworks, exams, depending on what you are lacking in grade. And also the same thing for your makeup. So I'm going to upload the grades substituted with the lower exam 2 grades if your grade has been higher. And after I do that, I give you back your exams and extra credit scantrons, okay? So last session, I had some students that they didn't get any of the extra credit points. And I'm suspecting the main reason is that they're not paying attention in the class. So if you're not paying attention, I ask you to just be yourself. What I mean is that, you know, if you're reading a novel, don't distract others. Or if you're playing on your phone, don't play something that others can see. Or if you're talking, I guess just talk with yourself quietly. Don't involve any other person, okay? Because overall, you will be hurting. But I don't want you to distract your friends, okay? And I can see from extra credits who didn't pay attention in the class. And I'm trying my best to make the lectures more interesting, so I attract your attention, okay? And I'm trying my best for all of us to have good grades, okay? So if I give you this and I say, is this orbital diagram consistent with Pauli exclusion principle? Yes or no? No, because we can have maximum 2 electrons, and each of these arrows represent an electron, and also they should be opposite directions, right? So this cannot be right. So this is Pauli exclusion principle. Any question about that? Good. Now, Hund's rule. Can anyone tell me what was Hund's rule? When we have orbitals with the same amount of energy, we fill them singly first, and then pair them up, okay? And one of your SI class leaders, we had like a meeting yesterday, and she told me in her class, she tells the students, it's as if I want to give you a handout, okay? First, I give each student one, and when I make sure everyone has one, I start giving again. Or I guess one other example can be candy, right? I have, candy I want to distribute to the class. First, I give each student one. When everyone has one, I start giving again, right? I don't want some people have like 2 or 3 and some others don't have any. So this is kind of similar here. First, when we have orbitals with the same amount of energy, like, P subshell that has 3 orbitals, right? Call this one orbital, Px, Py, Pz. When you want to put electrons here, first you put one in each of them, then you pair them up, okay? So if I give you the electron configuration for carbon, right? Carbon has 6 electrons overall, right? In the periodic table, you see carbon, the atomic number is 6. We put 2 in 1s, 2 in 2s, and now we want to put 2 more. So what we do, we start from here, and then after we put in Py, we're done. So if I give you this in the exam, and I say which one is the orbital diagram of carbon, and then one of the option is like this, which is the correct one, and then the other would be like this. Is this correct or false? False, right? Remember, your p orbitals, they have the same amount of energy, each of them. First, we fill them singly, and then we pair them up. In the case of carbon, in p subshell, we only have 2 electrons, okay? So is this obvious to everyone that why this one is not correct? Any questions? Okay. These were kind of review of the previous lecture. And also, I told you, just remember this. This is how we fill orbitals. We have 1s2, these 2's here. This means number of electrons. And this is the number of shell number, right? 1. And then s gives us the shape of the orbital, right? So we have 1s2, 2s2, 2p6, 3s2, 3p6, and then here we have an exception, 3p6, and then we go back to 4s, 3d, and 4p. And if you remember this, any element that I ask you in exam to write the electron configuration, you start counting the electrons and then see how many you want. And I'm going to solve more examples, so we'll be comfortable with this. Any questions? And just, anytime you have any questions, just raise your hand so I make sure that everyone knows things, okay? So now I have your extra credit quiz that I'm going to talk about because some students had difficulty and I want all of us know this for our exam, okay? So one question that I asked was that how many valence electrons sulfur has? So when we want to write electron configuration of sulfur, what is the first thing we do? We should know how many electrons we have, right? So you look at the periodic table that I give you in the exam. What is the atomic number of sulfur? Can anyone tell me? 16, right? So, as I told you, if you just remember these sequel that I'm going to write, 1s2. I told you this is the shell number. When n equals 1, whatever number is, we have to that number of subshells. So in n equal 1, we have 1 subshell, that is s. So if I write 2s, and each orbital has maximum 2 electrons with opposing spin, right? So when I write 2s, I'm in n equal 2. N equal 2, I have 2 subshells. What were they?
S and P.
Exactly. So I wrote already 2s, I write 2p. What is the maximum number of electrons in p? 6, exactly. So we don't have 2d or 2f. That was it, sp. Because n equals 2, we have 2 subshells. What about n equals 3? How many subshells do I have? 3, right? Whatever the number of n is, to that number you have subshells. N equals 3, we have 3 subshells, right? S, P, D. So I write 3s, 3p, and here I remember that I had an exception that 3d had higher energy compared to 4s. That's not what I meant. Let me have interesting color. Okay. So I fill out 4s first. So how many electrons should I put in 3s? 2. What about 3p? What about 4s? 2. What about 3d? Okay. So now, if you know this, as I said, this is universal. You can just remember that, and based on what element I give you in exam, you start counting electrons. So if you want to count electrons, you say 2 and 2 is 4. 4 plus 6, 10, right? 10 plus 2, 12 plus 6, 18. So we exceeded 16, right? We want to have, so first of all, I don't need to have these guys. And then here, I want to have 16 electrons, right, overall. I have 18. So how many should I put here instead of 6?
4.
Exactly. So let me write that again nicely. 1s2, 2s2, 2p6, 3s2, 3p4. Let's count. 2 and 2 is 4, 4 and 6 is 10, 10 and 2, 12, and then here I have 16 electrons, okay? And now here you can check if you write the electron configuration right or wrong. So whatever the highest number of n is, that is the period or row that your element is located in periodic table. So what is the period that this element is located at by just looking at this electron configuration? 3, right? That is the highest number you see. And then check, is sulfur in period 3? So we wrote it right? We start, so hydrogen and helium, they are in period 1. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, they are in period 2. And then sodium, magnesium, aluminum, silicon, they are in group, and then the others are in groups in the row or period 3. Does that make sense? So I told you something that I have in the next slide too, valence electrons. What was valence electrons?
The number of electrons in the outermost shell.
Exactly. So you look at what number here is highest, 3. And then you count the number of electrons, the overall number of electrons that exist in n equals 3. So here you have 2 plus 4, which is 6. And I told you that is your group number, right? So sulfur should be in group 6A. Is it? It is, right? Can everyone see that? Oxygen, sulfur, selenium, tellurium, polonium, they are in group 6A. So we wrote that correctly. And if you just know this rule, you don't have to even write the electron configuration. You see sulfur, you say, okay, sulfur is in group 6A, so it has 6 valence electrons. Any questions? And in order to progress with my lecture, for the other ones, I'm going to be faster, okay? So how many electrons exist in 3p subshell of chlorine? You write the electron configuration with the method I told you, but here I didn't ask for valence electrons. I told you, look at 3p subshell, see how many electrons you have there. So here in 3p subshell, we have 5 electrons, okay? So read the question well, see what I'm asking you. Am I asking you valence electrons, or do I ask something else? Are we good on this? Questions? What is the electron configuration of phosphorus? So phosphorus has 15 electrons. I guess that is a bad color. 15, right? So we say 1s2, 2s2, 2p6, 3s2, and then 3p3. So, and these questions were giving some of you a hard time, and I'm going to talk about them. Which of the following contradicts Pauli exclusion principle? So Pauli exclusion principle tells me that I cannot have 2 electrons with the same spin. Or other words, I cannot have 2 arrows that both are up or both are down. Or I cannot have 3 electrons or more in one orbital. So that's why this is wrong, but the rest are correct. Any questions? And for the next one, Hund's rule. Hund's rule tells me that first I fill out electrons, orbitals with electrons singly, then I pair them up. But what happened here? You know, here I didn't, the way to write this electron configuration is not correct because I cannot have, one electron here by itself without first I should pair this up and then write this. Besides, I also write 3s here to emphasize that this is not correct. Because you may argue that what if the element has lost electrons? If an element wants to lose an electron, it loses from the outermost shell. So I just wrote that to emphasize that this answer is really wrong. So this cannot be. Is that clear to everyone? Because I didn't fill them singly first and then pair them up. So I should have had this like that if I didn't have this. Does that make sense? So if we're good on that, I'm going to quickly go to the second version of the extra credit. So it's really similar to the previous one, as you see. If you know the other one, this one is pretty easy. What is the number of valence electrons in aluminum? Which group is it in? 3A, right? So the number of valence electrons is 3, as simple as that. And then if I ask you what is the number of electrons in 2p subshell of boron, you write the electron configuration, just see how many electrons is in 2p, which is 1 for boron. And then electron configuration of carbon, we just talked about it during the last class and also beginning of this class. We know how to write it, right? And then which one contradicts Hund's rule is, so Hund's rule tells me first I should fill orbitals singly, then pair them up. But here, this one doesn't have any electrons, so that is wrong. Does that make sense to everyone? And the next one, Pauli exclusion principle. Can I have 2 arrows in one orbital both up? Can I? No, right? So this is wrong. Okay. Any question about these questions? Good? Okay. Now, I'm going to, again, review some materials and add some materials. So as your friend mentioned, and I told you, the electrons in the outermost principal shell of an atom is called, or are called, valence electrons. Okay? So you write electron configuration, you look at the highest number of n that you have, count all the electrons, and that would be your number of valence electrons. Okay? Total number of electrons minus valence electrons would be core electrons. Or in other words, the electrons that are not in the outermost principal shell of an atom. Any questions? And this is important to know that valence electrons are involved in chemical bonding. I give you this as true or false. So I say, is the following statement true or false? Core electrons are involved in chemical bonding. True or false? false, right? That is valence electrons. Are we good with this? Questions? Okay, so I gave you two questions in your quiz. So if you have any questions, just let me know so I can explain so you can get those credits. Okay. Now let's write an example, right? Write an electron configuration for selenium and identify the valence electrons and the core electrons. What is the first step to solve this problem? Exactly, find selenium. Where is selenium? Group 6A. It has atomic number of 34. Okay. So, I think the easiest way is that you just write the order that I taught you and then count number of electrons. But you can just do it step by step too, whichever you prefer. So what I do, I just write this 1s2, 2s2, 2p6. I know I should have 2 subshells when n equals to 3s2, 3p6. I know here I have an exception, so I write 3d10 here. And then I know I have here, and I know I should have, you see, n equals 3, I have 3 subshells, s, p, d. And then I have here 4s, the maximum number of electrons is 2. After 4s, I have 4p, 6. So this one is universal. You can just write it for every single problem and then start counting the number of electrons, which we write as superscript. Here, these are electrons. And then it's a good practice to write this for all your problems. So in your exam, you don't have any issue writing this. Okay? If you write this, rest of it is just counting. Okay, so if you pay attention, you can easily answer this question in exam. So, 2, these are electrons, right? 2 plus 2 is 4. 4 plus 6 is 10. 10 plus 2, 12. Plus 6, 18. So till here, I have 18 electrons, right? And then here, I have 20. Here, I have 30, right? How many do I want to have? How many is if with this 6? So how should I change this to have 34? Exactly. If I change this, and then you can count again to make sure that you wrote that correctly. So it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. So what is the highest number of n you see here? 4. Exactly. So I have 4s2 and 4p4. So you should pay attention, although you wrote 3s first, but you count number of electrons in n equals 4 to report your valence electrons. So what is the number of your valence electrons? Exactly. As your friends say, 2 plus 4 equals 6. And you can check for your main group elements. So this tells me that these elements should be in group 6A. Is it selenium? So very good. If you find 5, and then you see selenium is not in group 5, you know that you did something wrong, okay? So now, what is the number of your core electrons? One way is to say that overall, we have 34 electrons, so this is the total number of electrons, minus 6 equals, what would that be? 28, right? So this would be number of core electrons. The other way is that anything that you see here that is not among your valence electrons, you count. 2 and 2, 4, 6, 12, 18 plus 10 is 28. Whichever is more comfortable for you, or is more convenient. Any questions?
I have a question.
Yes.
What's the reason that the 4s is or I guess that 3d is separated by the 4s?
So we fill out the orbitals based on their energy. So whichever has lower energy, we fill them first. So this is the order of their energy. Great question. Any other questions? And then to know why this orbital has lower energy, this deals with like quantum mechanical effects and then all the interactions between electrons and electrons. I mean, those things that we don't talk about in the class. But we fill out the orbitals based on their energy. Okay? Great question. Any other questions? Good? Okay. If no question, I also have like the answer from your book. Okay, and as I said, after we're done with the class, I'm going to, when I have access to my email and account again, I'm going to upload the lecture on Canvas. And also I add screenshots of your book, so I make sure you have all the materials that you need, okay? And I already uploaded all the study guides for all the chapters on Canvas and also previous year exams. So if you need like extra materials, you have tons of it. So just let me know if you have any questions. Some of the questions you see, if you were in the class, you paid attention, and you see something that you didn't talk about, that's because I didn't talk about them in this class. So I cut out lots of materials that I talked about in the previous semester, but the students were struggling, and I decided to just have like less materials to talk about in this class, okay? Any questions? Good? Oops. Okay. Now, if these are some examples of some elements in the periodic table, and I encourage you to write electron configuration for these elements, and then look at the similarities between them. As I told you, if you write electron configuration of elements in group 1A. So basically I said the reverse. I told you when you write the electron configuration, if you have only one valence electron, you know that your element is in group 1A. If you have 5 valence electrons, it means that your element is in group 5A. So by the same rationale, the reverse is correct too. So if you have elements that they are in group 5A, their electron configuration, so you have like 5 valence electrons, right? Here, or like for like phosphorus, the same thing. So when you add 2 plus 3, that adds up to 5, and that tells you this element is located in group 5A. And I told you this N here tells you the row or period that the element is located. So when you write the electron configuration, so if you practice this, you can see these trends. So for some of the problems or most of the problems that you see in the exam, you don't even have to write the whole electron configuration. You know that boron, you see, is in period 2, so it should end with 2. N equal 2 is the highest number that you have, and you know it's located in group 3A, so it should have 3 valence electrons. And you know we start with 3s, right? And it can have maximum 2 electrons with opposing spin, so 1 electron is left. So you have 2s2, 2p1. Just by knowing that, you can answer the question most probably in the exam that you see. Or like if I ask for fluorine, you know fluorine, if you look at the periodic table, is in period 2. So you know the highest number of N that you see here is 2. You know it's in group 7A, so it should have 7 valence electrons. You know 2 electrons go to 2s, so 5 remains. Is this obvious what I'm talking about here? Good? Question? Yes?
Does that rule apply to transition metals?
So I have in the next slide, I guess, yeah, here. I have transition metals. So transition metals are a little different. What is common in them is that they all have d orbitals. But we don't have exactly the rule that we have in main group elements. And that is a great question. And I'm not going to ask you transition metals. I mean, unless this is like really straightforward, you know, I'm not going to ask you. I focus on main group elements, okay? But great question. As you see here, we have all these strands, right? 2s2, 2p2, 3s2, 3p2, 4s2, 4p2. You see that based on what group you are, the electron configuration is the same in main group elements, just the row number is different, 2, 3, 4, and so on. But when you go to transition metals, you know, you don't have exactly the conventional trend that we talked about. So that's why I focus on main group elements. But it's important for you to know that transition metals are D block elements. What that means is that if you write the electron configuration, they have D orbitals. Or rather in their valence. Their valence electrons are also in D orbitals. Does that make sense what I'm saying? So here, you know, if you write, for instance, electron configuration of bismuth, in the core electrons or like inner shells, you also have D orbitals, but they are filled, and those are core electrons. But in their valence shell or their valence electrons are occupied in D orbitals. Does that make sense what I'm saying? So we're talking about valence electrons. And these are the ones that we wrote here and here. And remember, these are your main group elements. The rest are your transition metals. And then here, you have your lanthanides and actinides, which we don't talk about them in this class, so you don't have to worry about them. Any questions so far? Good? Okay. So now, let's work on this example. This question says, which element has the fewest valence electrons? So what is the number of valence electron of potassium? Exactly, it's in group 1A. What about boron? Exactly, group 3A. What about gallium? Exactly. What about calcium? What about oxygen? So which number is lowest? Exactly. You are also welcome to write the electron configuration and see that, but for the sake of time, I just progress with the lecture, so I have enough time for everything we want to do in the class. Now I want to talk about periodic trends. And what I mean is that, do you remember when we said that when Mendeleev put the elements based on increasing atomic mass, he saw certain properties reoccur periodically. And we said the modern periodic table is based on atomic number. But regardless, there are like some properties that are being repeated in each group of elements. Okay? And now what we want to study is that if we go up to down in each family or group in periodic table, or if we go left to right or right to left in each period or row, what happens to certain properties that we're going to talk about in this class. So the first one is atomic size. So what we want to know is that if in one period we go left to right, what happens to atomic size? Or if we go up to down in each family or group in periodic table, how atomic size of elements change. Is this clear what we want to accomplish? Okay. So first of all, we should define what is atomic size, right? So atomic size is determined by the distance of the nucleus from the outermost shell. For instance, if I have sodium, right? Sodium has 11 electrons. If I want to write Bohr model for the demonstration, right, or Bohr diagram. So if I have the nucleus here, what is the maximum number of electrons that can be in n equal 1? 2, right? And that is consistent with quantum mechanical model too. Remember 1s2. So what about n equal 2? What is the maximum number of electrons here? 8, exactly. 1, 2, 3, 4, 5, 6, 7, 8. So here I have maximum 2 electrons. Here I have maximum 8 electrons. And then in the next shell, I have only 1, right? Because 2 plus 8 is 10, so I have only 1. N equals 3. Okay. Any question about that? Now, let me write electron configuration for lithium. It's in the same group, as you see, right? And the atomic number is 3. So if I do that, so again, in n equal 1, I put 2 electrons, and then in n equal 2, I put 1 electrons. Which one do you think is bigger? Based on what I draw. So let me define, again, how we define atomic size. We define it by how far the outermost electrons are from the nucleus. So this is atomic radius. And then this is atomic radius. Which one is larger? Sodium is bigger, right? So when you have more shells, your atom is becoming bigger. Does that make sense? So in periodic table, when you go up to down, because number of n increases, you have more orbits or shell, atomic size increases. Okay? So what do you think would be the trend when you go left to right? We have the same number of shells, right? But if I have lithium compared to beryllium, beryllium has 4 electrons. So I do the same, I write this, n equal 1, and then I write here, n equal 2, 2, 3, 4. So in paper, you don't see much difference, and I wrote that like that intentionally. But the reality is that when you have only 3 electrons here, this electron can more freely move. Okay, it has more energy because it's not restricted by the nucleus or like other electrons. So what happens, it moves more freely, so the atomic size is larger compared to this one. Here, because we have like 2 electrons here and then 2 electrons here, it's as if the nucleus, there is like a balance between positive charge and negative charge, so the atom shrinks a little. But the difference is not as obvious as when we're moving in a group. In other words, your book has like this nice figure that has elements listed, and as you see, when we go left to right, atomic size decreases, atoms become smaller because now we have like number of electrons increases, so because of the positive charge of nucleus and negative charge of the electrons, the atoms become smaller. But as you see, the change is gradual, and if you just compare, for instance, these two, the difference is not that pronounced. But when you go in each family up to down, it's considerably, the atom becomes becoming larger. Does that make sense? Any questions? So if you know this trend, any question that I ask you, just look at your periodic table, and then you remember that anyone that is, or any element that is lower or like towards the end of each group. In other words, that higher n that is bigger compared to the one that has lower n. And then when you go left to right, atoms become smaller. Questions? So now I'm going to talk about a concept named ionization energy. And ionization energy is the energy required to remove one electron from an atom, and we define that in gaseous state. But the takeaway message is that the energy required to remove one electron from an atom. So I taught you before, and hopefully you know, that nonmetals, they gain electrons in reactions, right? For instance, fluorine, we didn't have F plus, we had F minus. So it likes to attract electrons. So do you think fluorine likes to lose electrons? So if I want, fluorine likes to attract electrons. So if I want to take one electron from fluorine, I should spend more energy. I should give it more energy. That's why fluorine has higher ionization energy compared to sodium, for instance. But sodium already wants to lose that electron, right? So just by a little amount of energy, sodium changes to Na+. So that's why, in general, metals have lower ionization energy compared to nonmetals. So if you consider this table, when we go up to down, ionization energy decreases. Okay? And that is really related to metallic character that I'm going to talk about next. Because when we go up to down, metallic character increases. And we know metals they like to lose electrons, so they more easily lose electrons. So that's why ionization energy decreases. They more easily lose an electron. And then when we go left to right, remember fluorine, for instance, doesn't like to lose electrons. It likes to gain electrons. That's why it has much higher ionization energy compared to lithium, beryllium, or like any other element on left. Are we good with ionization energy? So if I give you elements, you should be able, based on their location in periodic table, know which one has lower or higher ionization energy. Finally, metallic character. So metallic character is really related to ionization energy. So whichever element that has lower ionization energy, it means more readily loses the electron, so it's more metal. Okay? In other words, especially, the metallic character, the property is typical of a metal, right? Especially the tendency to lose electrons in chemical reactions. If you just look at the periodic table, here we have metals, here we have metalloids, here we have nonmetals. So we're talking about metallic character, so nonmetals have less metallic character because they're nonmetal, right? So if you just look at this, area here, you can say that when we go up to down, metallic character increases because we have nonmetal, then metalloids, right? And then nonmetals. Can everyone see that? Why metallic character increases? Because we have nonmetal, and then metalloid, and then metals. And then when we go left to right, metallic character decreases. You see here we have like metals, and then here we have metalloids, and then we have nonmetals. So left to right in periodic table, metallic character decreases. Questions? Are we good? Everything's crystal clear? Okay, so if everything is good, I'm going to ask your SI class leaders to come help me here. And as soon as you receive the tweet, you can just start answering. Do you have any extra? Everyone have one? Okay. Can everyone see the periodic table? And remember, in the exam, I don't have the atoms highlighted as metals, non-metals, and metalloids, so you should remember which ones are metals, which ones are non-metals. Did you have any extra quiz? Good. Make sure you note your name. Or you write your name. Thank you. And you have 5 questions, remember. I also wrote a note that go back to the
Got to put my name on it.
Just your scan. You have your name. Okay, perfect. Thank you.
I didn't write version number, was I supposed to?
Stop the lecture.